from me. I'll hand you over to Jack.
Hi, everybody. Yes, thank you for making the time to listen to me talk today. This will be about a 45-minute presentation with, as Amanda said, a Q&A session afterwards. Just to give you an overview, a lot of you signed up today, so we had well over 600 people sign up for this webinar. So I'm going to give a bit of a company overview just so that you guys understand what it is we do and how we work. We'll then drop on to the technology that we've used, PlumeStop, that can yield some pretty dramatic mass reduction in PFAS contamination. And then we will follow up with these two case studies from 2 UK airports. Then this will be followed up with a Q&A session. As Amanda said, those of you that don't get an answer, we will email our answer to you as part of that Q&A session. But just be mindful, a lot of people have signed up, so if we don't get round to you during this presentation, we'll absolutely follow up with you afterwards. So just a bit of an overview, Regenesis, what do we do? Regenesis is a company that specializes in the research, development, and commercialization of injectable substrates to remediate contaminated groundwater. So as a company, our focus is very much on groundwater. We've been doing this for over nearly 28 years now. And before Regenesis, nobody injected any proprietary reagents into the ground. We were the first company to research, develop, and commercialize and patent these sorts of reagents. And we comprise of engineers and scientists that develop these technologies, but also implement them as well. So we will actually come onto site and do those injection works for you. The technology that we're going to be focusing on today is PlumeStop. So PlumeStop is a colloidal activated carbon that was released in 2014. But that's not all, in terms of how we would work with you, it's actually quite involved. We're quite consultative in our approach. Typically what would happen is you'd come to us with a site and we would review the site investigation, the information that's already collected, and we would then decide if we could help you or not with that particular project. If we can, we'd then move on to a technology selection. That technology selection, today we're talking about PlumeStop and PFAS. What I'm talking about here is sort of the broader range of what we do. That technology selection would depend on things like the conceptual site model and what your commercial aspirations for the site are. We then give you a remediation design. So we'll write up a spec for you so you can understand how much it's going to cost, how long it's going to take, and what cleanup levels you can expect to achieve. And then we'll do the injection work as well. If you want us to, we can come to site, do those injection works. And also when it comes to post-evaluation, though it's not us that would be in direct regulatory liaison, it would typically be an environmental consultant. We do like to be involved in that process as well, just because we see this sort of data every day and we can give you some valuable input. So as a company, the idea is that we support you from cradle to grave with your projects. So that's a bit about us. Let's get on to the meat of it now. So PlumeStop and how it can treat PFAS in situ, drawing on these two case studies. So with PFAS, right now, the current default solution is pump and treat. And pump and treat has a series of drawbacks compared to PlumeStop, which is what I'm going to present today. First of all, pump and treat can be expensive to design and install. And really where the costs kick in is the operations and maintenance of these systems. They require fuel to run, somebody needs to maintain them, somebody needs to monitor them. Your capital expenditure during operation is significant. They'll also soon be generating hazardous waste. And it's very hard then, particularly when it comes to PFAS, to dispose of this hazardous waste. Indeed, in the US, they're starting to see bills being proposed to ban the incineration of PFAS because it's ended up being scattered all over towns. The reason for this, so very few options in terms of disposal. This is because the liability of PFAS, this forever chemical, sits then with the landfill or the incinerator. And also the pump and treat, that CapEx spend that you're doing whilst that system is running, will continue indefinitely. And ultimately, this can be not particularly environmentally sustainable if you look at the amount of contamination you're pulling out versus, say, the amount of carbon dioxide being created running this pump and treat system. So we have this solution, PlumeStop. Now, as I say, PlumeStop as a technology, it's been around since 2014, so it's pretty tried and tested now. It comprises of a liquid activated carbon or a colloidal activated carbon. What we've done is we've milled granular activated carbon down to 1 to 2 microns. So that's the size of a bacterium or a red blood cell. It's smaller than a pore throat. And what we've done is we've suspended it in a dispersive polymer. So by doing that, we've made sure that these carbon particles are charged in such a way that instead of sticking together, they repel each other and they stick to the aquifer matrix, creating this colloidal suspension. This means that you can inject it under low pressure and it distributes very far from each of those injection points, and it very quickly provides absorption sites. And ultimately, what you're delivering is you've converted the geology into a purifying filter in the subsurface, all in situ. As I say, it was launched in 2014, and we've had commercial applications ever since then, not just for PFAS, but for chlorinated solvent and petroleum hydrocarbon contaminated sites as well. But the R&D process going into producing this technology was quite extensive. Just to demonstrate, the power of colloids in the subsurface, what you're going to see in a second is PlumeStop on the left, and then you have powdered activated carbon, no dispersive polymer on the right. What you're seeing is a series of photographs taken over 12 minutes. And what we're doing is flushing just 14 pore volumes under gravity through each of those soil columns. And you can see that the PlumeStop has coated that soil column really well, whereas the powdered activated carbon with no dispersive polymer hasn't moved very far at all. So what does this mean at the micron level? So here we're at 50 microns. So there's your scale bar at the bottom, we're at 50 microns. These are your sand grains. They're very flat, not a lot of absorption sites, pretty low surface area. After the PlumeStop's been applied, what it does is it paints the subsurface with carbon. So you've created this purifying filter in the subsurface, greatly increasing its surface area, greatly increasing its absorption capacity. What you can see here are those 2 micron and below carbon particles coating this much larger sand grain. And you'll notice we've now dropped down to 20 microns across. To give you an idea, PlumeStop, for every gram of PlumeStop that you are injecting, gives you about 1,000 square meters of surface area that can be absorbed. The PFAS can be absorbed too. And what we're doing is we are utilizing PlumeStop to reduce or eliminate the environmental risk that PFAS poses. So if we just pause and we just think about those 2 words, remediation and environmental risk, the ITRC defines remediation as a process used to reduce or eliminate the risk for humans and the environment that may result from exposure to harmful chemicals. So it's the exposure bit that you guys need to remember, and risk. Okay. So what we're doing with PlumeStop is we are eliminating that exposure pathway. So risk is broadly hazard times exposure. The PlumeStop, when you inject it into the subsurface, binds the PFAS in situ, eliminating that exposure pathway. So you're breaking that source pathway receptor link, thereby eliminating the risk. And how we're doing this is that we are stitching PlumeStop barriers, we're injecting PlumeStop barriers on the down gradient edge of sites where there is a known point source of PFAS contamination. Typically, and in both of the case studies we're talking about today, they are fire training areas. So we are sequestering, we are stabilizing, we are absorbing PFAS in situ. This is a recognized remediation technique by the PFAS team at the ITRC. So the ITRC, the Interstate Technology Regulatory Council, sort of a widely respected body in the US. It often leads a lot of the charge when it comes to remediation. As a direct quote, groundwater containment may be achieved through the injection of an amendment that causes the PFAS to attach onto the materials in the aquifer. So this is what they've flagged as a remediation method, a suitable remediation method for PFAS, and it, to a degree, describes PlumeStop. So again, with this barrier, with this technology, what we're doing is we're installing a purifying filter into the subsurface. We're installing this barrier that as the groundwater moves through it, the PFAS is absorbed and effectively stabilized and retarded to slow that offsite migration of contamination. So what we're doing is we're creating this dynamic equilibrium, this absorption, and the effect of it is to increase the retardation of a PFAS plume. Now, PFAS under natural conditions maybe has a retardation factor of between 3 and 20. By injecting PlumeStop, you can increase that retardation factor by 3 to 4 orders of magnitude, which means that we have effectively sequestered it for decades. So here's the question: won't the barrier eventually fill up, and will you not begin to see breakthrough? The answer is yes, because PFAS doesn't degrade. But what's important is we know how long this will take, and that's super important. And so as well as spending a lot of money and time developing these technologies, we also spend an equal amount of time ensuring that we can design for them accurately. And this is what we've done. So we have a series of in-house models that incorporate PlumeStop absorption isotherms, so these Freundlich absorption isotherms. And what these models can do is predict the longevity of a PlumeStop dose. And that dose can be optimized to meet our clients' objectives. So what do I mean by that? What I mean by that is if we take airports, we're talking about airports today. If you take an airport, for example, typically that is the land use of that airport is probably going to stay the same for 30, 50, 70 years, particularly if it's a large major airport. In which case, it may be that that airport, particularly with everything that's gone on with COVID, in the immediate term might be low on funds. So they don't want to have the upfront capital expenditure of a barrier that might last for 80 years, 100 years, for example. Instead, then we could design them a barrier that lasts for 30 years. It has a much lower upfront cost. You then have very little costs other than monitoring after that barrier has gone in. And then in 30 years' time, we can cost forecast what the top up would be, and you could go and top up that barrier later on. So you can spread that cost or forecast for that cost, if you like. If you're looking to develop, then we can install a barrier that lasts much longer. In terms of this longevity and this modeling, this is something that's been extensively peer reviewed. This is true of all of our technologies. Lots of third-party papers have been published on this. This is one of them. We've had the University of Waterloo look at this, the University of Toronto, and as well as academia, the industry has looked at this. So a consultancy called Poor Water Solutions and a remediation contractor called In Situ Remediation Services have all reviewed the longevity aspects of this technology, with the conclusion that after a single injection, we can indeed stabilize this contamination for decades. If you'd like to read this paper, it's all available on our website. I will show you how to find that later on in this talk. So some of the benefits of this technology, PlumeStop, it's proven. So it's been completed on over 19 sites to date. We probably have closer to 6 years worth of validation data now, and it's backed up by numerous third-party academic papers. It's also effective. You can see the effect pretty rapidly, fairly immediately, and it gives this long-term protection, and it is available. We're not talking about something that's in the beta phases. We're not talking about a science experiment. This isn't a university commercializing a technology. This is a fully commercialized solution that can be brought forward to address these problems. It's also very safe to use. It's a non-hazardous product. It's the same material that you use for drinking water filters. No PFAS is brought to the surface, so that's key. Particularly, I know we've got quite an international audience today. In some countries, if you excavate or remove or bring contaminated material to the surface, you're required then to treat it as waste. Nothing's being brought to the surface here. We're also seeing no creation of hazardous breakdown products, and the time on site is minimized versus the amount of, the length of treatment you're getting. It's also sustainable. It's using organic, renewable activated carbon. So the original source of this would be something like coconut shells. It's passive as well. So I was talking about those CapEx expenditures for pump and treat systems. Once this is injected, particularly on a site like an airport where you might be doing routine SPMP groundwater monitoring anyway, all you would then need to do is monitor. So it's significantly cheaper if you look at total capital expenditure when you compare it to pump and treat. No waste is produced. We've explained why that's important. It's becoming increasingly difficult to find somewhere that would take that waste, and you have minimal disturbance to the site. So the actual injection and installation of these barriers, not just for PFAS, but generally, it's not unusual for us to be doing this on sites where they are commercially active. It's also quite adaptable. So it's not going to be a panacea for PFAS remediation. There's definitely going to be sites out there that we can't help you with. It's why that consultation bit that we do at the beginning of any project is really important. So it might be that it complements your existing remediation strategy. So it can be used standalone to sequester and treat a PFAS plume. You could use it just to protect a sensitive receptor, be that a stream, a lake, a river, or a abstraction well. Or you can use it in combination with other technologies like stabilization, excavation, or other pump and treat systems. But it is something that we take a lot of care and we do a lot of due diligence to make sure that this solution is the correct solution for that site. It's not a case of we would look at the site investigation that has been completed and then immediately go into full scale. There's a lot of work that goes into ensuring that this solution is the right one for that site. So there's a number of steps that we take. So we would initially undertake something that we in Regenesis internally call a DVT, or a design verification exercise. And this then links up with measuring the flux that's going across, the contaminant flux that's moving across the site. So what do I mean by that? What does a DVT involve? We're going to go into it, but it's essentially a very specific site investigation that gathers the data to inform the model that we're trying to build so that we can be sure that we have the correct plume stock dose for that site. We then combine this with flux measurements, because really that model is driven on flux, contaminant flux. So that's all about speed at which your groundwater is moving and the amount of contamination hitting that barrier, but also where is that flux occurring? Is this a fairly homogeneous aquifer, so there isn't any particular flux zones, or have we got something that's quite heterogeneous, so interbedded sands, gravels, and silts? And so it's really important to identify where those flux zones are so we can target them accordingly with the correct dose. We then feed all of this information in to our plume stock design, where we will look at things like competitive absorption, back diffusion. That's super important, particularly if, and it's often the way with PFAS plumes, we aren't able to install a barrier on the distal end of the plume. If we are having to essentially chop off the tail, if you like, for want of a better term, there will be some back diffusion occurring down gradient of that barrier. So we need to understand that, quantify it, and try and predict what that's going to look like, and ultimately calibrate our whole model. We then undertake some injection tests. The reason why we do that, we want to understand distribution, and then we would review all of this information to ensure that we have that solution for your site. So it's super important. So what do those work phases actually entail? So we'd have that design verification phase, all about making sure that we have the right information and that this solution is right for your site. We then have an installation phase. So not much to say here. This is where we install that barrier. Between those two phases, by the way, we may do a pilot, we may not. It will depend on what we think, if we think a pilot is necessary, or if a pilot is being asked of us. But say we go straight to full scale, we do that initial installation phase. Afterwards, there's a commissioning phase, and the objective of this commissioning phase is to optimize this barrier's performance. So we won't just install a barrier and walk away. We'll install the barrier, and then we will continue to monitor its performance and compare that against what our expectations of its performance. And if the subsurface, it's complex, if there is some underperformance or if there needs to be some tweaking, we can go back in and do additional injections to optimize the performance of that barrier to get it working. So there's two steps there. Then once that commissioning phase has been completed, the barrier is operational and monitoring can begin to demonstrate that long-term reduction in off-site migration. So what do we do during this DVT? So we'll do additional monitoring. So we will install more wells, and these wells have a dual purpose. You'll notice this as we go through the presentation, to gather baseline data. We'll do permeability testing. So this is sort of your run-of-the-mill sort of slug test, etc. And what we are trying to do there is understand the seepage velocity of the aquifer. For the groundwater sampling, so we won't just look at PFAS contamination, we'll also look at a wide spectrum of organic contaminants, because we need to understand any competitive absorption that's going to happen. We'll also install things called passive flux meters. We use iFlux here in Europe. There's lots of different suppliers out in the US. I find these valuable, and they're very useful for us in establishing exactly what the flux of contamination is moving across the site. Really useful tools, very easy to install. Yeah, gives us lots of valuable information. Sort of linking back to the additional groundwater sampling. To be honest, we're seeing it done more and more now as a standard way of investigating for PFAS, but we'll also do top assay testing because we need to understand what the total contaminant loading is going to be as well. We'll then do clear water injection testing and plume stop injections to confirm the radius of influence, because what we're trying to do here is construct a barrier. We're trying to build a wall, if you like. What we don't want to do is build a fence, so we don't want any gaps in the fence where contamination can get through. And it's a pretty straightforward exercise for us to confirm that we have the correct radius of influence. We can do colorimetric testing. Plume stop helpfully stains everything black, so we can take soil cores and be sure that we have that interlocking radius of influence. So we've done this a bunch of times across the world. I mean, we're involved in hundreds of sites when it comes to PFAS now. It's pretty unusual. I'd say I look at 30-ish sites a month. Not all PFAS, but I'd say of those, maybe 1 or 2 would be PFAS a month. So it's pretty unusual now for us within the UK, Scandinavia, and I know my counterparts across Europe, for us not to see a couple of PFAS sites cross our desk once a month. So we're involved in lots and lots of different PFAS sites. And as I say, we've completed over 19 globally. In terms of European firsts, the first time we did this was in Sweden at a port. We also then did an academic pilot study in Sweden as well. But the sites I'm going to talk to you about today are 2 commercial sites that we are currently undertaking here in the UK. So let's start looking at case studies then. So you understand how we get here, the due diligence that we do to make sure this is right. How does that actually play out? So these 2 case studies, there are 6-month pilot trials essentially across these 2 airports. This first site is an international airport here in the UK that has a fire training ground that's not only used for airport drills, it's also a commercial fire training ground as well. And it had a known PFAS issue since 2019. I'd actually say that this was probably the first PFAS site that I'd looked at in the UK, and it initially came across my desk in 2019. It's a voluntary scheme, so this airport is voluntarily remediating this site because there is a known triple SI across the down gradient of this particular site. So they're voluntarily cleaning this up. The geology isn't particularly interesting, although the May ground gave us some surprises. So river terrace gravels alluvium onto river terrace gravels onto London clay. Here we worked with ACON was the partner consultant, and thank you for this cross section. Groundwater is at approximately 2 meters below ground level, and the contamination, we had over 200 micrograms per litre of PFAS, and we also had some TPH in the mix as well. That's something that's quite common with PFAS plumes, particularly around fire training areas. They have to start the fire somehow, right? So often they're using gasoline to do that, and inevitably maybe some ends up in the subsurface. So we undertook this pilot trial. So here's your fire training ground here. This is the pilot trial area down there. And we tend to do this immediately up gradient of one of the historic wells that shows the highest levels of contamination on the site. Because if you're going to do a pilot, let's do it in the worst area, okay? Series of wells, we have borehole 12, which is 3.8 meters up gradient. We then have borehole 13, which is sort of your in barrier well to see how the barrier is performing. And then we have a series of wells down gradient. So FTG borehole 4, that is an historic well. So we had a lot of baseline data from this one. And then borehole 14 is an additional well installed another 5 or so meters down gradient of this barrier. So the idea is we've got historic data from borehole 4, and then boreholes 12, 13, 14, they are newly installed wells that have been sampled and characterized and tested as part of the DVT works, okay? We also did a series of radius of influence testing. So this ranges from taking soil cores to looking at color changes in the water. And here we also injected a parking agent into sort of down gradient of this barrier. So why did we do that? And what's a parking agent? PlumeStop is colloidal because of this dispersive polymer. I want to say colloidalness, but that's not a word. The ability for it to be a colloid is governed by this dispersive polymer, but this dispersive polymer breaks down over about 3 months. So PlumeStop isn't indefinitely colloidal, that's a better word. But here we wanted to control that migration of PlumeStop because there was a triple SI that was connected with a series of springs. And what we didn't want to happen is some of the water turn black down gradient of the site. Now, if that did happen, no toxicological issues. It's just not great PR if you turn water black in a stream. So that's why that parking agent was put in. So what were the conclusions of these works? So this site is a great example of why doing the DVT work is really important. The DVT did identify an increase in flux of PFOS and PFOA in particular, and these were our target compounds. This was then confirmed by those passive flux meters as well. So the iFlux meters you can see here, we can see that the flux was much faster than expected. There was quite an expense to do further site investigation. There was a lot of investigation had already been done, but this shows why it was valuable. These results, though, even though we saw this real high jump in flux, it didn't mean that we couldn't use PlumeStop on this particular site. And actually, we ended up increasing the dose of PlumeStop, but it had, I think it was less than a 5% impact on the total project costs. So the the value that these DVT works gave to us in terms of refining our design was huge. It's really a really important step. So in terms of the results, so let me just walk you through this graph. You've got these boreholes 12, 13, and 14 had 2 installs, one deep and one shallow. And then you have borehole 4 that just had a single installation. So 12 here, we are up gradient. Oh, sorry, we are up gradient of the we're up gradient of the barrier, and then we have a series of them that are down gradient. So we injected the plume stop. You can see concentrations dropped to rapidly dropped to below detection, and continue to be below detection even when that detection limit was lowered further in August. And they remain so down gradient of that barrier for the full monitoring round post injection. If you look at total PFAS, so this is also something that we looked at in the UK. We tend to be just regulated on PFOS and PFOA. What about total PFAS? We saw a greater than 93% reduction in some 11 PFAS compounds. Why is that important, particularly if you're from the UK, and why are we looking at the full spectrum? The reason for this is that you have different chain lengths and different compounds, and these different compounds have different affinities to sorbing to carbon, such as like your KOC, if you like. So as you move down this list, the KOC number gets lower. When you have something like PFHXA, for example, you wouldn't expect its affinity to sorb to carbon to be particularly strong, but here you can see that those concentrations were at or below detection limit. So the conclusions of that pilot trial, we saw a 99% reduction in PFOS and PFOA, down gradient of the barrier. We were able to make adjustments to the plume stop dose following those DVT works, so we could ensure that we could hit those limits. It confirmed that the barrier is working, and that the remediation solution for this site was suitable. And we're looking to roll this out as a full-scale solution towards the end of this year, completing it at the beginning of next year. The second site, another airport in the UK. This was the first site that we had ever done in the UK. Again, initially started off as a pilot trial. The full-scale works for this site are happening in a couple of weeks. So this is very much a live site. Here, again, like the previous airport, we had a fire training area, but they were looking to divest a significant chunk of this land for residential redevelopment. We had PFOS contamination around 320 nanograms per litre, and PFOA at 6,220 nanograms per litre. The geology here was a little bit more complex, so we had weathered chalk with some high permeability layers intermixed with that. And we had differentiating flux zones. We had some zones where it was showing very fast movement of contamination, and others where it was much slower. Groundwater was at about 3 meters below ground level. So we did design verification testing again, much like we did at the previous airport. Here we installed a iFlux into borehole 7. So similar setup as before. You have your up gradient well, borehole 7. WS05, that is a historic well. That's an important fact that will become evident in a minute. And then we have a down gradient well, and then a additional well 5 meters down gradient from that. So the iFlux data showed that we had two different types of flux zones, so really important. The DVT work in this case took about 10 days to complete. We observed no daylighting. What do I mean by daylighting? That's when this product erupts to the surface. All direct push injection rods were able to be advanced to 11 meters below ground level. So how we applied this, our preferred application method was viable on this site. Works were completed with no loss incidents. And in terms of things that we did discover, unlike at the previous airport where flux was a surprise, here we had we were surprised by the radius of influence testing. So the initial injections showed that we needed to increase the volume that we were injecting to get interlocking radius of influence. So that was a relatively easy thing for us to do. We had to mobilize some more product to site to do it, and we achieved the correct radius of influence. So yeah, we're trying to build a barrier, not a fence. So similar setup to that data before. So that shaded area there, that is up gradient. Then you have boreholes 8 with 2 installations, one deep and one shallow. That is 0.5 meters, 0.5 meters down gradient of the barrier. And then you have 2 installs, again, borehole 9 deep and shallow, 5 meters down gradient of the barrier. Now, what we found was up gradient, we had some pretty high levels incoming into that barrier. Half a meter down gradient of the barrier, we saw concentrations drop to near below detection limit. So we had a 99% reduction we had nearly a 99% reduction compared to borehole 7. So the barrier was working, it was stopping contamination. Borehole 9, that was down gradient of the barrier. In the deeper well, we saw declining trends, so that's all good. And however, in the shallower well, we saw a bit of noise, really, initially, when we were doing this pilot trial. We still saw a 65% reduction in mass compared to up gradient, but there was something going on, particularly in that shallow well. So we went back to the logs. And if you include WS5 in this, which is where the highest levels were recorded, WS5 was a historic window sample location. We had consistently higher results in this particular well, so greater than 1500 nanograms per liter of PFOA. It does appear to be decreasing. Initially, we were like, is the groundwater flow direction right? It's pretty unlikely. What's probably happened is that we've had some influence from the injections, so that's more likely. However, we didn't have any logs available for WSO5, so this hot well, but we did know that the base of it was at about 2.7 meters below ground level. So we went back to the DVT work to try and figure out what was going on. And you always go back to the logs whenever you look at a site. Start at the beginning where the data was collected. You look at what was recorded, and they did show that you had a slow influx of water in those shallower levels, and that at depth, groundwater appeared to be moving faster. The geology was more permeable. So what we thought was happening is that you had clean water arriving at this down gradient point faster. So that's why we were seeing this stronger declining trend. Whereas in the shallower levels, you still had a degree of back diffusion because the groundwater was moving slower. So to test this theory, we installed an additional well sort of at 2.5 meters down gradient of that plume stop barrier. And these were the results. So you can see immediately down gradient of the barrier, concentrations were reduced by 99%. Actually, as this pilot went on, borehole, the shallower install, we started to see a reducing trend, and we continued to see a reducing trend in the deeper well. But crucially, this new well that we installed returned levels that were below detection limit. So it enabled us to confirm our assumption. So that showed that the barrier was working, and it gave us the confidence to move forward to a full-scale installation. And this is what this full-scale installation will look like. It is a 277-meter long barrier. We're installing this barrier between 3 and 11 meters below ground level, and it will take, the installation works will take about 3 months, but with the installation and commissioning, we're looking at about a 7-month program to install this barrier. And this is also going to be a fully warranted solution, and all of the sampling is going to be done by the consultant we're working with, Mott MacDonald, as a third party. So we're doing a lot of sampling. We're doing a lot of due diligence here. We have a series of upgradient wells so we can monitor what the incoming flux is going to be during this installation and commissioning phase. We have a series of in-barrier wells, and the idea here is that they will verify the barrier's integrity, that it is working. And then we have a series of down gradient wells to show that you're getting this down gradient reduction. There's going to be a lot of sampling. We'll continue to do the radius of influence testing to ensure that we're getting interlocking radius of influence. There's a lot of due diligence, as much, if you like, is in the DBT work to make sure that we are installing a fully functioning barrier. And because we are doing such a high level of due diligence to make sure that this installation is correct, it enables us to warranty this solution. This warranty, we're calling it PlumeShield, so it's not a product, it's a commercial offering. And the idea behind it is that we have a simplified approach to better manage long-term liability and exposure around PFAS. So what does this warranty look like? Some people holding PFAS liabilities might be watching today. PlumeShield guarantees that our system will eliminate the environmental risk of PFAS in the groundwater. We'll provide you with a guaranteed price, so that includes time, the technology, PlumeStop, and the injection, so fully turnkey guaranteed fixed price. You'll get guaranteed effectiveness, so typically there's a retention. There'll be an upfront payment to cover mobilization, but only when that barrier is verified that it's working will you pay the final balance. So guaranteed effectiveness and guaranteed performance. So we will warranty that barrier for 10 years. If you want a longer warranty, we can do that. We can look at the site to see if that's possible. But typically the standard offering is a 10-year warranty. And if during those 10 years you see that there is breakthrough of that barrier, we as Regenesis will top that up at our cost. The reason we're able to do this is because of the way that we install these barriers. We internally have to produce a lot of information to show that we have installed them correctly. So if we've installed it correctly, we can verify it with our modeling. We have this much confidence in our technology, then why can't we warranty it? And that's what we're offering for PFAS sites. In terms of future developments, so what else is out there, current and future developments? If you are looking for resources on PFAS remediation, I'd encourage you to check out our website. Just go under resources and hit PFAS. Here we have probably over 13 hours worth of webinars on PFAS remediation by lots of different people, not just people talking from Regenesis. A wealth of third-party papers looking at this as a remediation method, as well as ways that you can reach out to us and contact us if you do have a site where you would like us to review this. We're also working with the University of Waterloo and a number of federal bodies out in the US, and we continue to provide a lot of support to academia internationally. But beyond this, we are also going to be releasing a new technology this year to address PFAS in the source zone. So we have a technology, PlumeStop, that is proven to be effective at removing PFAS from the groundwater, thereby eliminating the environmental risk. But we are also releasing another technology called SourceStop. So there's a link in those names there, that can be injected at the point source of the PFAS. So this can be injected into the groundwater, and it can also be mixed in the unsaturated zone as well. The idea is that we can then fully warranty a barrier that can capture that plume after that source has been stabilized. So we as a company can offer you a complete system. So in summary, Regenesis as a company, we offer a suite of remediation technologies for soil and groundwater. Colloidal activated carbon, or PlumeStop, is a proven technology with a long history of addressing contamination in situ. and that it can eliminate the risk that PFAS poses to the environment. We take a lot of time and effort goes into the due diligence of ensuring that PlumeStop is the correct solution for your site, and we do this through undertaking numerous design verification testing, and this is then backed up by third-party sampling. And because of the work that we do, we
Jack,
can.
you just I couldn't hear you for a few seconds, so you may just want to repeat your last sentence.
Sorry, can you hear me now?
Yes, can hear you now fine.
Yeah, all right, no worries. So because we do such a lot of verification that this has been installed correctly, it means that we can offer you a guaranteed approach. So yeah, that's everything from me. These are my contact details. Amanda, actually, could you post them in the chat in case anyone does want to reach out?
I'll do that in a minute.
No worries. Yeah, if anyone has any questions, please feel free to answer them now. I'll stop sharing screens.
Right, let me just post your contact details. There we go. You can find it in the chat details, in the chat box. In terms of questions, yeah, we've had a lot of questions already, but I just want to say I'll start asking Jack the couple of the first ones that have come in. But if some more come up, spring to mind, then do feel free to keep posting them, and I'll do my best to pick them up as we go along. Right. So let's look at the first one then. Yeah, this has come up a couple of times. Basically, people are asking about, does PlumeStop affect the permeability?
It doesn't. We've done hundreds of sites worldwide with this. It's a question that comes up quite a lot, to be honest with you, because we are just coating the aquifer with a 2-micron layer of carbon. It doesn't impact permeability at all. And even if you're using it to treat, say, chlorinated solvents, and you're trying to do some bioaugmentation as well with an electron donor, we don't get biofouling like you see in pump and treat systems. We're not impacting the permeability. In fact, we want it to stay permeable so it can be treated.
Okay, thank you for that. Right, let me just scroll down. Yeah, does there always need to be extra SI, so site investigation?
We do, yes, we do, particularly if you want the warranty, because we need to ourselves confirm the we need to confirm ourselves that the site is what you say it is. So we do need to do that. Yeah, it's just a matter of course. It's not that we don't feel like the site is. It's not that we feel like the site is under investigated. It's just we as a company have to do our own due diligence to make sure everything's correct.
Mm-hmm. Okay, so I've had that one already. Yeah, someone here, this was posted quite in the beginning. How long does PlumeStop last in the groundwater?
So it can last a very, very long time. So the PlumeStop itself will, we're talking hundreds of years to do that. What's different is that the retardation factor of the PFAS as that moves through the groundwater, that's really the bit that we are modeling in terms of time. So the PlumeStop itself is going to be active for hundreds and hundreds of years. It's the retention time is the bit that we're modeling.
Okay, and another, yeah, because you're talking about retention time, you've explained that, but somebody is asking, so the contamination is not destroyed?
No, it's the remediation technique is sequestration or stabilization, which is a pretty standard remedial approach. So you have cement stabilization. So what we are doing is installing a subsurface filter which removes the PFAS from the groundwater. So it's all about then protecting your sensitive receptors off-site.
Yeah, and I think you explained that later. Again, this question came in fairly early. Right, so let's skip a little bit then to another question. Yeah, how can you say that the concentrations will be maintained low over the years? And again, this is a question in different, that came in a different shape as well, but it sort of distills down to the same question.
So again, this is done through modeling and then confirming the modeling, and then long-term monitoring once the barrier has been installed. So
just to clarify, we wouldn't do the monitoring, right?
No, that's right. Yeah, so the monitoring, that's always done. All the results that we showed there, that was done by third-party consultants. So in the first example, we were working with AECOM, and then in the second example, we were working with Mott MacDonald. So yeah, all the monitoring is done by a third party.
Yeah. Okay. And yeah, this is another question that I've seen a few times. Can you use this on sites with a mix of contaminants?
Yeah, we can. So on the first site, we had some TPH in the groundwater. We can actually use a sort of separate technology to address that. But yeah, if there's a mix of other contaminants, then we can absolutely use it to address PFAS and probably those other contaminants as well. Where it has limitations, though, is if you have free-phase hydrocarbons, or free-phase anything really, in the groundwater, then PlumeStop isn't going to be an option. What you would need to do is address the free-phase element of that contamination first, and then you could take PlumeStop forward. But yeah, we can blend or combine different injectable substrates within a PlumeStop barrier to address whatever contaminant mix you have.
Okay, that's great. Thank you. I'm getting slightly overwhelmed with the questions here, so please bear with me. Let's have a look. Yeah, okay, this is about regulatory acceptance. How receptive were the UK regulators to using PlumeStop in this way?
The first site that we did, I appreciate that there was, quite a leap of faith taken. I mean, we did it in stages and in a pilot because it was the first time it was ever done in the UK. But overall, I would have said quite receptive, and I think it's because there's, particularly how we've done it to date with the DVT works, and then a pilot, and then we're going into full scale. Everybody's on that journey together, so they can see that the technology is working. I will say Mott MacDonald in particular did a great job of keeping the regulator informed all the way through, as did AECOM on the other side. And I think it's just about like dialogue and communication, and developing that strategy with them. But yeah, I'd say in the UK, I'm very receptive and open to this, in my experience.
Great. Yeah. Okay, let's keep going. Do we need to remove the activated carbon from the ground once it's exhausted?
No, there's no need to do that. The activated carbon, the PlumeStop, will absorb and retard the PFAS for a very long time. So this means that no excavation is needed. So there's no waste going to landfill, which is as I was sort of saying at the beginning, is becoming quite difficult to do.
Okay, just looking at the time. Yeah, we've got room for a couple more. There's definitely way too many questions to answer in the Q&A today, but don't worry, Jack will follow up with you afterwards.
I don't know if that's a good thing or a bad thing, but yeah.
Well, some are quite similar questions, so maybe we can
Yeah.
group them. But so we've had that one. Does it work with very low permeability or with very high seepage velocity?
Low permeability, you need to inject something into the ground, right? So if it is a solid clay and we're not going to be able to inject any liquid into the ground, then it's not going to be a viable technology for those sorts of sites. Likely though, you probably don't have much of a plume if that's what's going on. Sort of 10 to the -6 is a pretty good benchmark if you're looking for permeability numbers. It can work in very fast permeability, high seepage velocity sites, but it's all about flux, right? So it's about balancing that. So you might have a site where we can inject something into the ground, but the concentrations of PFAS are really, really high, which means that groundwater flow is slow, but the concentrations are really high, so we've still got quite high flux. The other end of that spectrum is real fast groundwater, but very low levels of contamination. So you might still have quite a high flux. So it's about balancing those two things. As I said, PFAS, it's not going to be the answer to everything. Plume stop, long day. Plume stop is not going to be the answer to every PFAS site. There's definitely a defined treatment envelope, but we'll work that out in the site evaluation phase.
Okay. Right. Let's see. Do you have any other European cases, or are these the only 2 sites?
They're the only 2 sites written up for now, but I'm sure that'll change. We've got quite a bit in the pipeline, so yeah, watch this space, I guess, is that.
And
But
there
yeah,
are
in
American
terms of
sites as well.
oh yeah, loads of lots of American sites. Again, all of that can be found at the website if you're looking for more information on case studies.
Right, I think we'll do 1 or 2 more, depending on how long your answers are. How do the monitoring requirements differ from cement stabilization?
That would depend on your that would depend on the country in which you are, I suppose. Yeah, that's a real hard one to answer without knowing sort of where you're from. Like neither of them are in both examples, in both technologies, you aren't removing the contamination. So I would imagine it could be quite similar, as you would, yeah. It would depend on the country that you're in. But I'll pick that up with you maybe later on, and once I figure that out, I'll give you a better answer to that.
Okay. Did I ask this one already or not? Do we need to remove the activated carbon from the ground once it's exhausted?
Yes, yeah, we talked through that one.
Yes, I did. Okay, sorry. Yeah. Okay, I'll pick one towards the end. Okay, there's 2 good ones. We'll do 2 more. What is the key thing which is often missing from the site investigations that you require to do your own testing, verification testing?
So I'd have said, I don't know, like 2 years ago would have been top assays. That's something that was often overlooked because it can be or was quite expensive. Now it's just passive flux meters, really. Even if all of that information is there in one form or another across the whole site, we'd still want to do further testing so we can offer this warranty. And again, that's not a criticism of the investigations that we're seeing. It's just that we're looking for different things. So yeah, I'd say what you typically miss is sort of passive flux testing, really. In saying that, just picking that up, if you do think this solution is an option on a site that you're working on, if we can work with you during, say, your first rounds of site investigation, and we can almost blend in a DVT with those additional site investigation works, that could then negate the need for further investigations later on down the line. So it's always beneficial to engage with us as early
actually,
as possible.
I just saw a question about this that I wanted to ask anyway. So it says here, can remedial investigation be done in parallel with the pilot test, or does it need to be done in advance? So this is pilot test, I suppose they're talking about.
Pilot test. Yeah, I think it depends on the site. Probably is the answer, as long as there's a bit of expectation management. So ideally, you'd want to do DVT pilot if we thought it was necessary, or if other people wanted the pilot to be done, we can do the pilot, and then you'd go full scale. If you did sort of DVT additional investigation with the pilot at the same time, then if the pilot fails because we find out something in the DVT, then it'd just be making sure that everybody understands why. So it could be done, but it's not preferred.
Okay.